Okay, let's dive into something really at the forefront of computer science and software engineering right now.
Sounds good.
Look around us. I mean, literally every single day, we've got satellites, sensors, drones, just capturing petabytes of information about our planet.
It's an absolute explosion of geospatial data, yeah.
And that sheer scale, right? The
Yeah,
complexity of all this location-specific info, it's just, well, it's starting to overwhelm the traditional ways of analyzing things.
absolutely. We're kind of drowning in data, but still finding it hard to get the insights out efficiently.
Exactly. So how do you even begin to make sense of it all? And this is where foundation models are popping up, the AI tech behind things like large language models.
Mhm.
They're being talked about as a potential game changer, specifically for analyzing all this geospatial data.
That's the idea. And in this deep dive, we're aiming this specifically at you, pulling together insights from the stack of sources you gave us, research papers, project descriptions, blog posts,
Yeah.
the works.
Right. Our mission here is to really unpack geospatial reasoning with these AI foundation models. We want to explore, what are these models? Who's actually building them?
What can they do? Because some of it sounds pretty amazing.
Definitely. But also, just as importantly, what are the unique challenges? Because the real world, the geospatial world, it's messy, right? It's not just text.
It really is.
Yeah.
So, yeah, we'll get into the tricky parts, too. There were some genuinely fascinating details, and maybe even some surprising facts that jumped out from the source material.
Okay, so first things first. What exactly is a geospatial foundation model? Let's just break down that core concept to start.
Well, if you think about foundation models generally,
Hmm.
the sources describe them as these really large-scale deep learning models.
Huge models.
Huge. And their power comes from being pre-trained on just massive, massive amounts of diverse data.
Mm.
Because they've seen so much, they learn very general patterns and representations.
Which means they're super adaptable, right? You don't need to build a whole new model from scratch for every single task.
Exactly. You can often fine-tune them for lots of different specific jobs
Yeah.
with minimal extra data, or sometimes you just show them a few examples. That's the whole few-shot learning thing.
Okay, so then a geospatial foundation model, or GOFM, just applies that idea to location data.
Precisely. These are FMs that have been specifically trained on enormous amounts of geospatial stuff. Satellite images, aerial photos, maybe topographic maps, environmental sensor data,
Yeah.
even like street-level views.
And the why here seems really key. Instead of building one AI model just to spot floods, and another one just to map crops, and another one for something else,
Right.
the GeoFM learns the fundamental patterns across all that location data. It's learning about the Earth itself.
Yeah, it's about learning a kind of a generalized understanding of the planet's surface, its features, how things change over time, and that general knowledge can then be a starting point for almost any specific geospatial problem you throw at it.
Yeah. Learning transferable geospatial knowledge. Okay, that makes sense as the basic idea. So, who's actually building these things? What kind of projects are out there? The sources highlighted a few different groups.
Yeah, there are several interesting efforts. One really significant one that focuses on Earth observation is this collaboration between NASA Impact, IBM, and Clark University. They've developed models like Prithvi-EO.
Ah, yes, Puthio-EO. That's a great example. A GeoFM trains specifically on Earth observation data, right? Using that harmonized Landsat Sentinel data, HLS.
Exactly, HLS multispectral data, which means it's seeing the Earth in different wavelengths of light, stuff beyond what our eyes perceive, and it's doing this over huge areas, repeatedly.
And the scale you mentioned, Prithvi-EO 2.0 was what considered the world's largest geospatial AI model at one point.
That's what the Clark University source pointed out, yeah. Trained on something like 4.2 million global time series samples from that HLS data. It wasn't just looking at static images. It was learning from how places change over time and incorporating location context right into the learning process. Pretty sophisticated stuff.
So, did training at that massive scale actually pay off? Did it lead to, better results in the real world?
It certainly seems like it did. They showed some really significant improvements in critical tasks, like
Right.
mapping how far floods spread or identifying burn scars after wildfires much more accurately.
Okay.
And the sources mentioned it outperformed, I think, 6 other geospatial foundation models in standard remote sensing benchmarks. So that suggests the huge pre-training really did capture valuable transferable knowledge about the Earth.
That's the whole promise, isn't it? That generalized knowledge paying off.
Yeah.
The clock team even took it further, right? Applying it to specific tasks.
Yeah, they fine-tuned it for things like filling in gaps in satellite images where there are clouds, or classifying different types of crops over a growing season. And apparently, Fine-tuning Prithvi consistently gave better results than trying to train a specialized model from scratch for those tasks.
And they're also working on explainable AI, XAI, trying to peek inside the model.
Yes, and that's fascinating. They're developing benchmarks to understand how these models make decisions. Are they actually learning the underlying physics and geography, like the unique spectral signatures of different materials, how things naturally change season to season, the spatial relationships between objects?
Because you need to trust these things,
Yeah,
especially for critical applications.
exactly. Understanding why a model gives a certain output is crucial for users to trust it and choose the right tool for their job.
Okay, switching gears a bit. Google Research seems to be coming at this from a slightly different angle. They're focused on mixing FMs with generative AI, like LLMs, to speed up geospatial problem solving.
Yeah, Google obviously has this incredible foundation of geospatial data already with maps, Earth, Street View, and so on.
Right.
Their research seems focused on leveraging FMs with that data and, importantly, allowing people to interact with it all using natural language.
Using models like Gemini, their big language model. So the idea is Gemini becomes the front end.
Kind of, yeah. You could ask it questions in plain English instead of needing specialized GIS software or coding skills to manage complex geospatial data and analysis workflows.
And they've also built their own remote sensing FMs, trained on high-res imagery.
Yes, models trained specifically on very detailed satellite and aerial images, often paired with text descriptions or labeled objects within the images. So these models are designed to really understand what's in those high-res pictures.
And you can fine-tune those for tasks like mapping every single building or road,
Oh,
or assessing disaster damage quickly.
exactly. Those are key examples. But where it gets really interesting, I think, is what they call their geospatial reasoning framework.
Okay, tell me about that.
The sources describe it as using a model like Gemini to actually orchestrate the analysis. It acts like a conductor.
Okay.
It connects different specialized AI models, taps into various data sources, Google's own huge data sets, maybe your private data, public data archives, and it does all this based on natural language queries from the user.
So can you give an example? That hurricane crisis manager, one from the source.
Yeah, that was a great illustration. Imagine you're managing disaster response. You could use this framework to first say, visualize the area before the hurricane using satellite data from Earth Engine.
Okay.
Then overlay high-resolution aerial photos taken after the storm. The remote sensing FMs could automatically detect damaged buildings or flooded zones. Maybe you pull in predictions from their WeatherNext AI about where flooding might get worse.
Right. And instead of needing complex tools to put all that together,
You can just ask Gemini things like, okay, estimate the percentage of homes damaged in this specific neighborhood, or based on demographic data over here, suggest where we should prioritize sending relief supplies first. The LLM understands your goal and directs the right geospatial tools and data to answer it.
wow, that really lowers the barrier to entry. They mentioned testers like Airbus, Maxar, Planet Labs are already playing with this.
Yeah, big names in the satellite imagery world are exploring these capabilities through their trusted tester program. It shows there's real interest.
Now, another name that came up was Stefano Erman, co-founder of Atlas AI and also at Stanford. They seem to be pioneers in this space, too.
Absolutely. Alice AI is very focused on that intersection of geospatial data and deep learning, particularly FM's Erman's lab at Stanford develops SatMe.
SatMe, right. That was highlighted as the first FM trained specifically for satellite imagery using a self-supervised approach.
Correct. The goal there was really enhancing image recognition, helping the AI spot subtle patterns or anomalies in satellite photos that might be missed by traditional computer vision methods, things that indicate change or risk.
And Atlas AI sees a few key application areas for these GeoFMs.
They do. Forecasting is a big one, using the time series nature of satellite data to predict things like crop yields, environmental changes, or even societal trends.
Makes sense.
Enhanced image recognition, building on models like SatMe is another key area. And then there's this really powerful concept they call contextualization.
Contextualization, what does that mean here?
It's about integrating different types of data, so not just analyzing the satellite image in isolation, but combining it with, say, text descriptions, economic data, weather patterns, using the multimodal capabilities of these models.
Oh, okay, so you could ask it more complex things in natural language.
Exactly. Like, show me all the new construction sites near major rivers in Southeast Asia over the last 2 years. The AI needs to understand the query, analyze images, perhaps cross-reference with other databases, and then give you the insight or alert quickly. It's about understanding the image in context.
making the insights much faster to get to.
Yeah.
Okay. And then there was one more, quite different type mentioned, spatial LM.
Yeah, spatial M is different. It's described not just as a language model, but as a 3D foundation model. It's built specifically to process 3D point cloud data.
Point clouds, right. That's like the data you get from LiDAR scanners. Millions of 3D points representing a space.
Exactly. Or from RGBD cameras, or even reconstructed from multiple video frames. It's this raw, unstructured 3D data. Spatial LM takes that in and generates a structured understanding of the 3D scene.
Structured meaning it identifies things, like walls, chairs, objects.
Precisely. It can output things like identified architectural elements, put 3D bounding boxes around objects, and label them semantically, knowing that cluster points is a chair, that plane is a wall, that opening is a door, all within the 3D scan.
The potential applications there seem huge for things like robotics, self-driving cars.
Absolutely. Autonomous navigation, understanding built environments for architecture or construction, creating detailed digital twins for simulation.
The user discussions in the sources even mention things like an AI assistant that remembers where you put your keys by understanding your home's 3D layout. Or better AR/VR experiences.
Yeah, some really exciting potential uses, though it was also clarified that spatial LM primarily needs that 3D spatial data as input, not just standard images. And there was, some user discussion about whether the accuracy currently matches specialized 3D processing tools. But the core concept of a foundational AI model for understanding 3D space is definitely a crucial piece of this whole puzzle.
So when you pull all these different threads together, the Earth observation focus, the high-res imagery plus LLMs, the 3D understanding, the combined promise of these GOFMs starts to look really powerful.
Incredibly compelling, yeah.
What are the big overarching benefits, then, if you synthesize across these projects?
Well, one of the absolute biggest is efficiency. GeoFEMs promise to drastically cut down on really labor-intensive, expensive manual data collection and labeling that's always been a huge bottleneck in geospatial work.
Because the model's already pre-trained on the world, right? It knows a lot before you even ask your specific question.
Exactly. Then there's improved consistency. Models trained on these huge, diverse global data sets tend to perform more consistently across different regions and time periods compared to models trained only on limited local data.
And that leads to this really powerful idea mentioned, unified representation, creating these unique numerical embeddings or fingerprints for every location on Earth.
Yes. And these embeddings aren't simple. They capture really complex, multifaceted characteristics of a location, its land cover, climate, infrastructure, maybe even hints of economic activity.
So they can serve as this common foundation for totally different applications, like predicting species habitats and modeling disease spread using the same underlying location understanding.
That's the idea. You can compare places based on their deep characteristics, their fingerprint, not just surface-level attributes. It opens up new ways to find correlations and patterns.
They also seem good at bridging modalities, understanding the links between different data types.
Especially the multimodal ones, helping the AI connect, say, what a tree looks like in a satellite image versus a street-level photo versus maybe a text description. That's really vital for building comprehensive digital twins of environments.
And finally, they just unlock new capabilities, things that were really hard or maybe impossible before.
Yeah, things like advanced semantic understanding, using these location embeddings to add context to text analysis, or super fast similarity searches. Find me all locations globally that are similar to this specific place. And agile modeling, speeding up the creation of new specific geo-AI tools because you're just fine-tuning the big GeoFM, not starting from zero.
So the potential is massive, making complex geospatial insights faster, easier, more accessible. But the sources were also very clear that this isn't easy. There are some unique, tricky roadblocks with geospatial data.
That's right. Current FMs, even the advanced ones, run into some real challenges here.
Like what?
Well, first is the sheer multimodality and integration complexity. GeoAI isn't just text and images. You've got text, yes, but also multiple types of images, remote sensing with many spectral bands, street view photos. You have knowledge graphs, time series data, and crucially, geospatial vector data.
The points, lines, and polygons that actually define features on a map, the core geometry.
Exactly. And the challenge highlighted is that even current multimodal FMs often struggle to really deeply, seamlessly integrate with that fundamental vector data. Understanding where something is precisely, its shape, its geometric relationship to other features, that's critical for true spatial reasoning, And it's still hard for many FMs.
Which leads right into the next point, spatial reasoning limitations. You mentioned LLMs are getting good at the text side of things.
Yeah, the sources, like that archive paper, show they can be surprisingly good at geospatial semantics, recognizing place names in text, describing features using language. They can sometimes even outperform specialized models with just a few examples. They understand the words about places.
But.
But that same paper showed they really struggle with precise spatial reasoning that's actually grounded in the real world. The example is pretty stark. GPT-3 could identify place names correctly, but when asked to predict their geographic coordinates,
It was way off.
wildly off,
Yeah.
sometimes hundreds or thousands of miles wrong. It violated basic geographic principles, like things nearby being related. It even generated coordinates that weren't geographically valid, like impossible latitude-longitude combinations.
Wow. So it knows the word Paris, but thinks it's in the middle of the Atlantic.
Sort of, yeah. It shows a fundamental gap between processing language about geography and truly reasoning within geographic space. It doesn't have that grounded spatial awareness yet.
Okay, that's a major hurdle. What else?
Another big one is geographic bias. Like all FMs, GeoFMs can inherit and even amplify biases from their training data. But here, it has a specific spatial dimension.
Meaning if most of the training data comes from, say, North America and Europe,
Then the model might perform much worse or make unfair assumptions when applied to regions in the global south where high-quality labeled data might be scarcer or just look different.
so the model becomes biased towards data-rich areas.
Precisely.
Yeah.
And figuring out how to detect and correct those geographic biases in these enormous complex models. That's a really significant technical and ethical challenge. We need models that work fairly everywhere.
Makes sense. Then there's spatial scale.
Right. Geospatial information exists at all sorts of different scales simultaneously.
Yeah.
A city might be just a point on a global map, but it's a complex area with internal streets and neighborhoods when you zoom in.
And the GOFM needs to handle that, understand the right scale for the question being asked.
Yeah, it needs to manage that variability and ideally infer the appropriate level of detail for a given task, which isn't always straightforward.
And lastly, this tension between generalizability and spatial heterogeneity.
It's a tricky balance.
Yeah.
You want the model to learn general patterns like what forests typically look like, how rivers behave, common urban structures. That's the power of generalization.
But the real world is also incredibly varied locally. Every forest, every city block has unique characteristics. The model needs to capture those broad trends without washing out the important local details that make places unique. Finding that sweet spot is tough.
So quite a few significant challenges to overcome. But despite that, the overall feeling from the sources seemed pretty optimistic about the future, especially around convergence.
Absolutely. Multiple sources really highlighted the integration, the coming together of large language models and these geospatial foundation models as the next really big leap.
Combining the LLM's strength in understanding language and complex requests with the GeoFM's deep understanding of the physical spatial world.
Exactly. That combination holds the promise of making geospatial insights way more accessible, more actionable for a much broader audience, not just GIS experts. Think scientists, policymakers, businesses, maybe even the general public.
And the research is pushing hard on those challenges we just talked about. Definitely. Improving how FMs handle all the different geospatial data types, especially vector data, boosting their actual spatial reasoning chops, finding ways to mitigate geographic bias, making them generalize better across diverse environments and scales. That's where a lot of the cutting-edge computer science and engineering work is happening right now.
Okay, so we've journeyed from this problem of just overwhelming amounts of geospatial data to the rise of these powerful new AI foundation models designed to fundamentally change how we analyze and understand our planet and the complex environments we build on it.
Yeah, it's clear the potential here is immense, especially as these GeoFMs get hooked up with generative AI, letting us query them using natural language. But as we discussed, there are still significant technical hurdles. Data integration, true spatial reasoning, fairness, bias, that are active areas of research.
It's a fascinating field because the AI isn't just number crunching or processing text. It's attempting to model and reason about the real physical world we all live in.
Yeah.
And as these models get better and better at that, understanding our world not just on a flat map, but in 3D, across time, integrating all sorts of data. Here's maybe a final thought for you to take away. How might this evolution change things, not just for the experts tackling global challenges or for industries using this data, but maybe, potentially, how you personally interact with, navigate, and understand the very physical spaces around you every single day?